Okay, in section 9.3, we're going to apply hypothesis testing or significance tests to means. I'm going to break this up into two different sessions, though, because there's a couple extra wrinkles. Number one, we have to revisit the t-interval, or the t-distribution, rather. We're going to always use the t-distribution for means. But then also the situation where we have matched pairs, right? Because right now, we're only looking at really one population or one sample. So if we have two lists, we need to turn that list into one list of differences. So we'll look at that in the second part, right? What I want to do in the first part here is just think about running a significance test from start to finish. We'll look at the hypothesis test template to help us out with that, and do that start to finish for a one sample mean. So in the first example here, we're not going to actually do the hypothesis test start to finish. We're just going to think about our conditions for inference, which anytime, so like when we get to an example later where it says, do these data provide convincing evidence, right? Do these data convincing evidence? Anytime you see that, that means you're going to carry out a significance test, or you're going to carry out a confidence interval, something start to finish, and you should use either the textbook author's state, plan, do, conclude method, or use one of my templates that I put out, and make sure you cover everything that's in either one of those items. Right, so, but here all I want to do is really just one part of the template, right? Anytime we did a confidence interval, and now anytime we do a hypothesis test, we should talk about our conditions for inference. So let's look at the research question here. A classic rock radio station claims to play an average of 50 minutes of music every hour. So we don't have to do the hypothesis test, but we can see right away they're claiming that that the average is 50. And we want to think about a null and alternate hypothesis. However, it seems that every time you turn the station on, there is a commercial playing. To investigate their claim, you randomly select 12 different hours the next week and record what the radio station plays in each of the 12 hours. Here are the number of minutes of music. So, again, thinking about an alternate here, you wouldn't really be questioning this if they were playing more than 50 minutes. You're feeling like they're playing less than 50 minutes. So that's how we would come up with our alternate hypothesis. Just something to think about in the back of our minds there. So what are our conditions for inference? Well, we need to take a simple random sample so that we get a representative sample. And it says that to investigate their claim, you randomly select 12 hours, right? So we'll put in quotes, randomly. Anytime a condition like that is explicitly stated for me in the narrative, I just put it in quotes. That covers that we were able to identify that was important. And we took 12 different hours, right? So 12, there's certainly more than 120 hours in a week, right? So our condition there is for independent observations, right? So we have first condition SRS. We want our observations to be independent of each other. We wouldn't want to take 12 consecutive hours, right? They wouldn't really be independent of each other. But we sampled less than a tenth of the population. So lowercase n, my sample size, is less than a tenth of capital N, the population size. Okay? Now, for the last part, this is a little bit more work on our part. We have to look at these 12 numbers and determine, do we think that they follow a normal distribution? There's two ways we can do this, right? Both would involve your calculator. You're going to put the list, actually three ways. We could make a histogram, we could make a box plot, which is generally going to be my choice, or we could make a normal probability plot. If you remember all the way back from chapter 2, the normal probability plot, that is going to plot z-scores and raw scores. And if it's roughly linear, then we can assume we have a normal distribution. So a little bit of review of that. But I wouldn't suggest making the normal probability plot. I'll show you how to do it on the calculator, but I think our best bet is always use that box and whisker plot. It's also the easiest one to draw, like rather than a histogram or even a normal probability plot. So I have to go to my calculator. And on the calculator, we go to Stat, and we select Edit. So the very first thing we're going to have to do is take those listed numbers and put them in the calculator. So I want to go over so L1 is highlighted like that, and just press Clear. Right, now I'm going to enter the 12 numbers that I have on my worksheet. 44, 49, 45. 51, 49, 53. 49, 44, 47. 50, 46, 48. So the box plot is going to be really easy to make and really easy to sketch because we can use our trace feature. So I'm going to hit second y equals. That's my stat plot option if I want to make a graph of my data. Second and y equals. And I'm going to use my first plot, and I'm going to turn that plot on. Okay. Now, like I said, if we wanted to make a histogram, we have the histogram option right here. I'm going to choose to use the box plot, but I'll show you all three. So if I select a histogram, remember your shortcut to getting the graph, we hit zoom 9. Okay, so there's my histogram. Looks like there might be a gap. Looks like it might be slightly skewed to the right. And again, this is why I like the box plot. It's going to be much easier for us to tell shape. Then your normal probability plot. Remember, in this situation, it is a scatter plot, but it's this very last one here. I'm going to press enter, and we're going to put the data on the x-axis, and the y-axis will be the z-scores. We can switch that if we want. I'm just going to hit zoom 9 and enter, and it looks like so it looks like you got your z-scores on the y-axis and your raw scores on the x-axis, and I don't see any really departures from linearity. So if you were going to sketch a normal probability plot, make sure that the x-axis says, the times, right? These are number of minutes of music per hour, so you could just put time there or minutes, and then up here you put z-scores, and then just draw a rough sketch of it. But I think that our box plot is the easiest, best option here. So I come down here, and I'm always going to select the box plot with the extra dots, because if there are outliers, it will plot them for me, and we know that's going to be important for our normality assumption. So overall, it looks like it's roughly symmetric. You can see that little bit of a tail to the right that we saw before, but no major concerns here in terms of using the t-distribution. Remember, t-distribution is a robust distribution. So if our sample size is 12, we have 11 degrees of freedom. That is a less normal, it's a wider, more variable distribution than an exactly normal distribution. So our assumption for normality doesn't have to be super precise. We just kind of don't want to see any outliers in this box plot. So if I hit the trace button, this will allow me to get a scaled graph of my box plot. The minimum is 44, so I'm going to draw that for my box plot. So when I write my condition for normality, I need a graph. Okay, and this was the same for confidence intervals. We just didn't have to do it a whole lot. So the minimum is at 44. Then we come back to the calculator and arrow over, and we can see that the Q1 is the very short distance here, 44 to 45.5. And I kind of use that scale to help me gauge, how far out to go each time. So if that's 1.5, I want to be consistent with the rest of my differences when I'm sketching the graph. But I have the calculator to kind of help and guide me here. And then this goes up to, this is going to be a jump to 48.5. That's where the median lives. So that's kind of, at least twice as much as that first jump, because that's 3. So that's 48.5. And then we have sort of a shorter gap here in the next one, up to the Q3, which if I keep moving along here, that's 49.5. And then finally, we have our last whisker. Like we said, that's a little bit longer, but nothing to be super concerned about. The max is 53 minutes. That was the maximum amount of minutes of music they played, right? So we want to write a conclusion here. Since the box plot is roughly symmetric with no outliers, the t-distribution is appropriate. And you want to make sure that you do all three of these things. So the hardest part for means is when we have a list of raw data like that. Usually if we have a big sample size, if the sample size is over 30, we don't have to do this. If our sample size is small and we have the raw data, we have to make a graph. And I think the box plot is the easiest graph to make. And now the next example, they just complete the significance test for us. They take the sample mean 47.9, subtract the hypothesized mean of 50, and they find a test statistic of negative 2.59, and they say use table B to find the p-value. So they don't give us an exact p-value. They say, the p-value is going to be between 0.01 and 0.02. Well, where are they getting that from? Let's look at our t-distribution. If we scroll down to it, remember there's two normal distributions. Then we get to our t-distribution, and in particular, I want to use 11 degrees of freedom. So what happens with 11 degrees of freedom? As I move over to the right, I don't see 2.259. That's the test statistic they got, negative 2.59 rather. So when I look along here for a 2.59 at 11 degrees of freedom, I don't see it, but I know that it would be somewhere in between these two values here. You can lock in and see. Right? 2.59 lives between 2.328 and 2.718, so that's why they're saying the p-value ought to be somewhere between 0.02 and 0.01. But we'll be able to use the calculator for our test, so we'll get an actual p-value. So this would be significant at 5% level of significance, but not significant at a 1% level of significance. So that's basically what I'll do in the next two examples. I don't have to use the table. I'm going to use my calculator. So here I have a null hypothesis, mu equals 10, and an alternate that it's greater than 10. So this is a right-tailed test. So the p-value only lives in one tail. Sample size is 75, so that means my degrees of freedom is 74. Let's keep that in mind. All right, so the test statistic is 2.33. So what am I looking for here? I'm looking for the area to the right of 2.33. So I'm going to use my calculator. It's going to be TCDF, just like normal CDF, except it's a t distribution. We're going to go from 2.33 to somewhere really big, like 100. We don't have to put in mean and standard deviation. Okay, the standard deviation changes for the t distribution always for your degrees of freedom. So all we need to communicate to the calculator is our degrees of freedom in that situation. So if you don't remember where TCDF is, it's second. You hit the second key and the vars key for your distributions. And you're going to see number 6 is TCDF. So we had 2.33. We picked an upper limit of like 100. And our degrees freedom is sample size minus 1. In this case, it was 74. And so I get should be a pretty small p-value, 0.01127. Now in part B, it's going to look a little different because it's our two-tailed test. So even though our test statistic falls below the null hypothesis, we have a test statistic of negative 0.51. Our p-value is actually the area in both of these tails because our result could have been above 0.51 as well. That's what we agreed to when we set out for a two-tailed test. So the easiest way to get this one would be just subtract the area that's not shaded. So I'm going to do 1 minus TCDF from negative 0.51 to positive 0.51, and I'm going to use my degrees of freedom. The sample size was 10, so I have 9 degrees of freedom. And we get a pretty large p-value, 0.622. So clearly we wouldn't reject the null hypothesis there. We don't have significant evidence that the mean does not equal 300. And in the first one, it would depend on our significance level. And the next example is kind of our worst case scenario for a hypothesis test for means, and that's because there's 24 numbers, so n is less than 30, which means we have to make a graph. And we see, do these data provide convincing evidence? That means we have to do a hypothesis test from start to finish. Okay, so let's think about the research question here. Abby and Raquel like to eat sub sandwiches. However, they notice that the lengths of the 6-inch sub they get at their favorite restaurant seem shorter. It's huge. This is how we come up with, when people ask me, how do I know my alternate? We read. Seems shorter. That's indicating a left-tailed test. Okay, so that's going to be really important. To investigate, they randomly select 24 sandwiches, and then they get the length. So I'm going to lean on my hypothesis test template here, and this is the way I usually like to work through these. So my first thing I do is state the parameter of interest. This is mu. It's the true mean length of 6-inch subs at this restaurant. And we start with that. Null hypothesis is always a statement of equality. The restaurant says they're 6 inches. Okay, these two young ladies believe they're shorter. Okay, so we have to identify that and pull that out of the context. All right, we need to look and see if they selected a simple random sample. So we come back to the narrative. It says that to investigate, they randomly selected 24 different times in the next month to order a sub. Right? So we can put in quotes, randomly selected. And they did them at 24 different times, but so those are our randomly selected subs. Okay, our 24 is less than a tenth of the population. Right, easy to assume there. And then for normality, we have to make a graph. So we're going to go ahead and do that. So you can't, when you do this, I'll have people do this, I guarantee you, on the quiz and the test. They'll say the graph is approximately normal or symmetric, and then they never sketch it. You have to give me the sketch of it. So we do get a very symmetric box plot. The min is 4.5. I'll write that down. And then my Q1 is 5.25. Pretty almost exactly symmetric in the middle there. They're like the same length. So the median is 5.625. Pretty small spread in the middle. And then Q3 is 6, which is what they're supposed to be. And then the max was 7. Okay. So, and then make a statement about that. Okay, we're able to say there that the box plot is roughly symmetric, and I provide a graph of it as well. Okay, this is a t-test. Right. Remember, on the formula sheet, the formula is right there. May not write it exactly the way I'm going to write it, but it's there. It's the statistic minus the parameter. And if we already explored what the difference between a statistic and a parameter is, we should be fine. Standardized test statistic minus parameter. So I'm not going to write statistic minus parameter on this template. The t-test is the statistic. So the way I get t, the t value, is I take the statistic, which is x bar. I take the parameter, which is mu, and I divide by the standard deviation of the test statistic. Okay, so over here, I'm just going to have my calculations. I'm going to tell you what the t statistic is and what the p-value is. And then down here, we'll interpret those. Okay, so remember, for this problem, I had the actual 24 numbers, and I went to stat and edit, and I entered them. So now, when I go to stat and test, and I select number 2 for my t-test, I'm actually going to tell the calculator that I have the data. Okay, I am not going over here to stats. If I had the stats, that would be a situation where it's going to ask me for mean and standard deviation, and I could get those because I have the data in my calculator, but I have the actual data. It's in list 1, so I'll change that when I get to it. But the null hypothesized value for the average was 6 inches. I want to make sure I hit second in the number 1 here so that the calculator knows my data is in L1. And remember, the girls are particularly interested in whether or not these subs are less than what is claimed, less than 6 inches. So when I calculate here, I get a t statistic of negative 2.407. Okay, so with degrees freedom 23, don't really have to write that, but I'm going to because that's where the p-value comes from. P-value depends on our degrees freedom. My p-value is 0.012. So when I come back to the original problem, notice that alpha was 0.1. That's pretty high alpha level. Remember, the 0.1, 10%, that means that if you did this test many times, then 10% of the time you're going to conclude that the sandwich shop is making sandwiches less than advertised, and you're going to actually be wrong if the null hypothesis is true. So that's a pretty large alpha value. Usually you want to use 5 or 1%. So if my p-value is 0.012, for alpha of 0.1, 10%, remember the mantra, if the p-value is low, the null must go. Well, 0.012 is lower than alpha. Low is relative, but it's always compared to alpha. We would reject H0. Okay, what does that mean in context? It means the girls have significant evidence that the sandwiches are shorter than advertised. Okay, so this is convincing evidence. So they verified their hypothesis. Now, the second part of this is realizing that we could be making a type 1 or type 2 error here. And since we rejected H0, there's only one type of error we could possibly make here. When we reject H0, only a type 1 error is possible. Okay, the type 1 error is when we reject the null hypothesis when it's actually true. The type 2 error happens when we fail to reject the null hypothesis and it's actually false. So since we rejected H0, only the type 1 error is possible. And we want to talk about what that means in context. So explaining what this would mean in context would be that we conclude that the sandwiches, basically that the restaurant is falsely advertising their sandwiches to be 6 inches long when they're really not. So the restaurant probably would not be happy with this conclusion, especially if it's wrong, if they're really sincerely making 6 inch sandwiches and we concluded that they're not, it's a wrong decision. So remember, if you want to compare that to the justice system, a type 1 error is like putting an innocent person in prison or finding that they're guilty when they're innocent. And the type 2 would be finding that a guilty person is innocent incorrectly, right? Those are your errors. The other options would be that we made a correct decision.